Welcome back to the AIR Prep series. In our last session, we did a detailed walkthrough of the AIR exam itself, the structure, the three domains, how scoring works, and what to expect on exam day. So if you haven't watched that one yet, I'd recommend going back and starting there because it gives you a really useful map of everything we are going to cover in this series. Now, with that map in hand, today we are going one level deeper into the content itself. We're going to look under the hood of AI because domain 1 of the AIR exam assumes a foundational understanding of how these systems actually work. And that's exactly what this session is designed to build. I know what some of you might be thinking. I'm a risk professional, not a data scientist. Why do I need to understand how machine learning works? Fair question. Here's my answer. You don't need to build these systems, but you absolutely need to understand how they think, where they can go wrong, and what questions to ask when you're auditing or governing them. Think of it this way. You don't need to know how to fly a plane to be an aviation safety regulator, but you do need to understand enough about how planes work to know when something is unsafe. Same principle applies here. So in this session, we are covering three things: machine learning, deep learning, and the AI lifecycle. And throughout, we'll keep asking the same question. Where is the risk? Let's get into it. Let's start at the beginning. What actually is machine learning? Here's the official definition. It's a subset of AI where systems learn patterns from data without being explicitly programmed. But let me break that down in simpler words because that definition can feel a bit abstract. Imagine you want to teach a child to recognize dogs. You could write a rule book: four legs, fur, barks, tail. But that gets complicated fast. What about a three-legged dog, a shaved poodle? Instead, you show the child thousands of pictures. This is a dog, this is not a dog. And over time, the child's brain figures out the pattern on its own. That's machine learning. You feed the system data and it figures out the rules itself. Now here's where it gets interesting for risk professionals. Traditional software does exactly what you tell it to do. Machine learning software does what the data tells it to do. And that's a crucial distinction. Because if your data has gaps, biases, or errors, your model will learn the wrong patterns, confidently, at scale. I was working with a retail client whose demand forecasting model had been trained on 3 years of sales data. What they hadn't accounted for was that 2 of those years were pandemic years. The model had learned pandemic-era buying behavior as normal. When things returned to normal, the forecasts were way off. The data taught the model the wrong lesson, and no one caught it until the shelves were either empty or overstocked. That's the risk hiding inside machine learning fundamentals. So now that we understand what machine learning is, let's talk about the different flavors it comes in, because the type of ML being used tells you a lot about where the risks might show up. The first type is supervised learning. Think of this as learning with a teacher. You give the model labeled examples. Here's an email and it's spam. Here's another and it's not. The model learns the difference. Most of the AI tools you encounter in business, fraud detection, credit scoring, medical diagnosis, use some form of supervised learning. The risk here? The labels. If the historical labels are biased or incorrect, the model learns to replicate those biases. Then there's unsupervised learning, learning without a teacher. Here, you don't give the model labels. You just give it data and say, find the patterns. Customer segmentation tools often work this way. The risk? You don't always know what patterns the model has found or whether those patterns are meaningful or spurious. Reinforcement learning is a bit different. Imagine training a dog with treats. The model takes actions, receives rewards or penalties, and learns to maximize the reward over time. This is how game-playing AIs and some robotic systems work. The risk here can be quite subtle. If the reward signal is poorly designed, the model finds shortcuts you never intended. And then there's semi-supervised learning, which is a mix. Some labeled data, lots of unlabeled data. Common when labeling is expensive or time-consuming, like in medical imaging. Each of these approaches has a different risk profile. Knowing which one is being used is the first question a good AI auditor should ask. Now let's talk about deep learning, because this is where AI really starts to feel like magic. And as risk professionals, anything that feels like magic should make us slightly nervous. Deep learning is a subset of machine learning that uses something called neural networks, layered structures that can identify extraordinarily complex patterns. It's what powers facial recognition, voice assistants, large language models, and medical image analysis. If machine learning is learning from examples, deep learning is learning from examples at a much more complex, multi layered level. Here's an analogy I like. Regular machine learning is like teaching someone to identify wine by giving them clear rules: color, aroma, taste. Deep learning is like training a master sommelier who has tasted 10,000 wines and now just knows. They can't always explain why they know, they just do. That's the power of deep learning. And that's also its biggest risk. The computational requirements are enormous. You need huge data sets, and crucially, the decision making process is nearly impossible to fully explain. I've sat in meetings where a bank's model risk team was trying to get a deep learning model approved by their regulator, and the regulator kept asking, "But how does it make its decisions?" And the honest answer was, "We know it works, but we can't fully trace why." That's not a comfortable place to be in a regulated industry. Deep learning delivers remarkable capability, but it demands exceptional governance. Let's zoom in on neural networks for a moment, because understanding even the basics will make you a much more effective AI risk professional. Neural networks are loosely inspired by the human brain. Our brains have billions of neurons connected to each other, passing signals. Neural networks mimic this with layers of mathematical nodes. You have an input layer where data goes in. You have hidden layers where the processing and pattern recognition happens. And you have an output layer where the decision or prediction comes out. Here's a practical example. Imagine a neural network trained to detect fraudulent transactions. The input layer receives transaction details: amount, location, time, merchant type. The hidden layers process these inputs through thousands of calculations, adjusting weights based on patterns it has seen in historical data. The output layer produces a score. This transaction is 94% likely to be fraudulent. Now, here's the key insight for risk professionals. Those hidden layers are where the black box lives. You can see what goes in, you can see what comes out, but what happens in between is extraordinarily difficult to interpret. This is why explainability is such a central challenge in AI governance. And here's something that often surprises people. The network learns by getting things wrong. It makes a prediction, compares it to the correct answer, measures the error, and adjusts its internal weights accordingly. This process, called backpropagation, happens millions of times during training. The risk? If the training data doesn't represent the real world accurately, all those adjustments are calibrated to the wrong reality. The network becomes very confident at being wrong in a very specific way. Now let's shift from the technology itself to how AI systems are built and deployed over time, what we call the AI lifecycle. And this is where the risk conversation gets really practical for auditors and governance professionals. Think of the AI lifecycle like building and operating a commercial aircraft. You start with design and engineering, you test extensively, you certify it, you fly it, and then you monitor it continuously for its entire operational life. A problem at any stage can be catastrophic, and problems in early stages often don't show up until much later. The AI lifecycle typically has 5 phases. Problem definition, where you decide what the AI should do and whether AI is even the right solution. Data collection and preparation, gathering and cleaning the data the model will learn from. Model development and training, building and training the model. Testing and validation, checking whether it actually works as intended. And deployment and monitoring, putting it into production and watching how it performs in the real world. Here's what I want you to take from this slide. Each of these phases introduces different types of risk, and those risks compound. A bad decision in the problem definition phase can undermine everything that follows. Poor data preparation creates a flawed foundation. Weak validation means problems reach production undetected. And lack of monitoring means problems that emerge post deployment go unaddressed. As a risk professional, your job is to ask, at which stages does this organization have controls? And which stages are flying blind? More often than not, the later stages get the most attention, and the early stages, which are arguably the most critical, get the least. Let's talk about the data phase in more detail, because in my experience, this is where the most consequential AI risks are born and also where the least amount of governance attention tends to be paid. The data phase is where you collect, clean, label, and prepare the data that the model will learn from. It sounds almost administrative, but the decisions made here echo through the entire life cycle of the model. Start with data quality. Incomplete records, outdated information, measurement errors, all of these teach the model the wrong patterns. Then there's bias. If your training data reflects historical inequalities, who got hired, who got approved for loans, who received treatment, the model will learn to replicate those inequalities. It doesn't know they're unjust, it just knows they were the pattern. And then there's representativeness. I worked on a project for a logistics company building a route optimization model. The training data was largely from their operations in Western Europe. When they deployed it in Southeast Asia, where road conditions, traffic patterns, and seasonal factors were completely different, the model performed terribly. The data wasn't representative of the deployment context. Privacy is another big one in the data phase. Are there personally identifiable data points in the training set? Is the data being sourced and retained in compliance with GDPR or other applicable regulations? And finally, data lineage. Can you trace exactly where every piece of training data came from? If you can't answer that question, you can't fully assess your model's risk profile. The data phase sets the ceiling for everything that follows. So the data has been prepared. Now we move into actually building the model. And this phase has its own distinct set of risks that risk professionals need to understand and probe for. The first one is overfitting. Imagine a student who memorizes the exact practice exam questions instead of understanding the underlying concepts. They ace the practice test but fail the real exam. That's overfitting. The model performs brilliantly on training data but poorly on new real-world data. The flip side is underfitting, where the model is too simplistic to capture meaningful patterns at all. Getting this balance right is a core model development challenge, and poor calibration here directly impacts real-world reliability. Then there's explainability, which we've already talked about, but it's worth emphasizing again here. During model development, developers often face a trade-off between accuracy and explainability. More complex models tend to be more accurate but less explainable. In regulated industries, that trade-off has compliance implications that need to be explicitly managed. Algorithmic bias can also be introduced at this stage, not just through data, but through the choice of algorithm, the way the optimization target is defined, or the way performance metrics are selected. If you optimize purely for accuracy without checking whether that accuracy is consistent across demographic groups, you may be building in discrimination without realizing it. And then there's documentation. I've audited AI development processes where the model had been through 7 iterations, but there was no record of why certain design choices were made, what alternatives were considered, or what the model's known limitations were. That's not just a governance gap, it's a risk management gap. You can't manage what you haven't documented. Your model has been built, it's been tested, it's been approved, and now it goes live. You might think the hard work is done, but in many ways, deployment is where the risk story really begins. The most insidious deployment risk is model drift. The world changes, consumer behavior shifts, economic conditions evolve, regulatory environments move, and the model, trained on historical data, starts to diverge from current reality. This can happen gradually, almost imperceptibly. And because there's no error message, no system alert, it can go undetected for a long time. Integration with legacy systems is another common pain point. Most enterprises don't run purely modern infrastructure. AI models often need to connect with older systems that weren't designed for this kind of interaction. Data formats don't match, latency issues emerge, edge cases that worked fine in the test environment break in production. I've seen AI deployments delayed by 6 months, not because of anything wrong with the model, but because of integration challenges with a 15-year-old ERP system. Security is increasingly a concern too. AI models can be targets for adversarial attacks, where malicious inputs are designed to fool the model into making incorrect decisions. And then there's the human oversight question. In the rush to scale AI, organizations often reduce the human review layer. Automated decisions go out without any human check. When those decisions are wrong, and they will be wrong sometimes, the damage is already done before anyone notices. Deployment is not the finish line, it's the starting line for operational risk. So we've deployed our model. Now what? This is where monitoring and governance come in. And frankly, this is where most organizations are still playing catch up. Continuous performance tracking means watching your model's outputs in production on an ongoing basis, not just whether the system is technically running, but whether it's producing outputs that are accurate, fair, and consistent with what was validated before deployment. Think of it like the instruments on a plane's dashboard. You're not just checking that the engine is on, you're tracking altitude, speed, heading, fuel levels, all in real time. Regular model retraining is essential. As data patterns shift, the model needs to be updated to reflect the new reality. But here's a nuance that often gets missed. Retraining is itself a risk event. A retrained model is effectively a new model. It should go through the same validation rigor as the original. I've seen organizations retrain models quarterly with almost no documentation or revalidation, essentially deploying new models without realizing it. Incident response is something very few AI governance frameworks have addressed adequately. When an AI model produces a harmful or incorrect output, what's the playbook? Who gets notified? How quickly can the model be rolled back or overridden? How are affected parties informed? These questions need answers before an incident occurs, not during one. And underpinning all of this is governance. Clear ownership, defined accountability, audit trails, escalation paths. Without a strong governance framework, monitoring is just data collection. It's the governance layer that turns observations into action. Let's bring everything together. We've covered a lot of technical ground today, and I want to leave you with the practical lens to carry forward. Machine learning is the engine driving modern AI. It's powerful because it learns from data, and it's risky for exactly the same reason. The quality, representativeness, and integrity of training data directly determines the quality and fairness of the model's decisions. Deep learning takes this further, delivering remarkable capability in handling complex, unstructured data, but at the cost of explainability and interpretability. As a risk professional, every time you encounter a deep learning system in a high-stakes context, your first question should be, how do we explain this model's decisions to regulators, customers, and the board? The AI lifecycle is where risk lives, not in one place, but distributed across every phase, from how the problem is defined all the way through to how the deployed model is monitored and governed. Controls need to exist at every stage, not just at the end. Data quality is not a technical nicety, it is a foundational risk control. Poor data is the single most common root cause of AI failures, and it's often the least governed. And finally, governance is what makes all of this responsible and sustainable. Technical controls alone are not enough. You need clear ownership, documented processes, continuous oversight, and the organizational culture to act when something goes wrong.